The demand of commodities, fine chemicals, aroma compounds, proteins, or medicines such as antibiotics is increasing worldwide. However, conventional biotechnology production processes based on monocultures of microbial flora are reaching their limits. So how can new, more efficient production routes be created by scale-up that not only meet demand, but are also economically viable and sustainable? Roughly speaking, this is what the DFG Priority Program Interzel is about. We will be exploring this topic piece by piece with our podcast, Lab Whispers about bioengineering. In the pharmaceutical industry, the efficient and reliable production of new biological active ingredients is of enormous importance. This can accelerate drug development and shorten the time from idea to market launch. Immunoglobulins are in great demand in medicine. The CHO Life Plus project, which is funded within the DFG Interzel Priority Program, aims to use and optimize cell lines for the production of the immunoglobulin IgG1. One challenge is to find efficient scale-up strategies to transfer the processes that work well in the laboratory to an industrial scale and vice versa. A team of researchers is on a mission to find out more. Today we are talking about this with Professor Dr. Ralf Takors, University of Stuttgart, and Professor Dr. Michael Schlüter, TU Hamburg. Thanks for being here today. Would you like to briefly introduce yourselves?
So hi, thanks a lot for having us. So my name is Ralf Takors, and I'm heading the Institute of Biochemical Engineering here at the University of Stuttgart. And I'm really happy to collaborate on that said project together with Michael.
Thank you, Ralf. So my name is Michael Schlüter. I'm the head of the Institute of Multi-Phase Flows at the Hamburg University of Technology. And with my group, we mainly do research on bubbles in liquids, which are necessary to keep the organisms alive in these big reactors. And we're very happy to do this together with Ralf, who has a competence in the microorganism part.
This is fascinating for sure. What fascinates you the most about the program?
The program gives us the possibility to collaborate, to see what's happening on large scale, to bring it down, to bridge then all these orders of magnitudes the cells have to manage once something has been developed in small scale, and to make it happen on large scale. And that program enables us to do exactly this, which is typically otherwise hardly be funded by other possibilities.
I totally agree with that. We have knowledge and experiences on transport processes in these gas-liquid flows for chemical industry and biochemical industry, but we do not work with any cells. And so to bring these points together, to tailor the transport processes on all scales and understand what's going on in these large-scale reactors, and see how does this influence at the end the outcome for a product that is gained by biotechnology. So we don't have any experience in biotechnology, and we would not be able to do this kind of joint research without this program.
Well, I'm going to skip right to the question of the experimental multi-scale analysis. So what is that, and why is the simulation of lifelines in bioreactors important?
Multi-scale means if you imagine you are a cell in a reactor and you are breathing like in reality, like you are breathing, so you need oxygen, and the oxygen has to be provided into the water phase somehow. And the way how we provide the oxygen is we transfer it from a gas bubble to the liquid phase and to the water phase. And this means that we have to transfer the oxygen from bubbles in very tiny distances, we call this boundary layers on a micro scale, through the large scale reactor, several meters in height. This is a very, very large scale. And so we have to bridge these different scales from the very tiny way to the large scale industrial reactor system. And this is, you can imagine, quite challenging. And this is what we mean with this multi-scale approach. And this is, on the one hand side, difficult from experiments, but it's as well very difficult also from the modeling and numerical simulation point of view.
Yes, indeed. And another, let's say, aspect of the multi-scale view is also the possibility to scale something which is happening in large scale down into the lab, which means that, we want to prevent that there are some developments in the lab which at the end of the day are not realized in large scale because something happens that deteriorates the performance of the cells while scaling up. This is why it is important to check before the cells are really scaled up into a large scale, the performance of these cells in small scale. And this is why we care for somehow mirroring these large scale conditions in small bioreactors, already giving us then the information that we want to see whether the cell is stable enough or not for the large scale application.
And industrial scale bioreactors often have cultivation conditions that exhibit spatial and temporal gradients. How can this limit the production performance of microorganisms? And how can your research contribute to the understanding and optimization of processes in bioreactors?
Yeah, this is something, again, thinking about you yourself as a cell, and think about what you like. You like to have ideal conditions, maybe a little bit warm outside. Then you need to have a little, let's say, ideal conditions in terms of oxygen supply and things like that. And now what happens when you go into a large scale, you do see not always the ideal conditions around you, in particular when you're flotating around as you do as a cell. And that means that the cells adapt frequently to these changing environmental conditions, and that simply costs energy, and that simply may then induce some regulations inside the cells were not made for. And to know about that, what is happening inside the cell, and then to see that, for instance, in small scale, and to do something against that these not that much liked performances are then happening in large scale, this is exactly what we are heading for. We want to see what the cell do. We want to measure what the cell experience, and then ideally do something against, such that the performance of the cell in the small scale is really the same one as that in large scale, that there's no bad surprise happening later on. That's the idea.
Back to the large scale, as you now see, we need to know how the cell moves on their trajectories through the reactor, how it's flowing around in the reactor. But you have to imagine these reactors in industrial scale, they are intransparent. They are from stainless steel, so you cannot look inside. And it's even because everything has to be very pure and clean, it's not allowed to have any special insights into these kind of reactors. So this is a challenging point. And therefore, we use this transparent reactor and also Lagrangian sensor particles that are floating in the reactor, measuring the different parameters so that we know how the cell feels on this trajectory. So we call this lifeline of the cell, by the way, because it's what the cell experienced during its life. And then we transfer this lifeline to Ralf's group. And this is the idea for getting insights into this multi-scale approach and to find these gradients for temperatures, concentrations, pH, for example, shear stress, and so on.
So you're meeting some challenges now through the transparency. Are there other obstacles that you need to work on?
Yeah, especially for these Lagrangian sensor particles that we use to measure what the cell feels. You can imagine it's difficult to get a particle that is as small and light as a cell is. And this is the biggest challenge right now, to miniaturize these sensors and to make them in the same way following the flow than the real cell is following the flow. So this is one of our biggest challenges right now and the biggest obstacle.
Yeah, and from our side, it is to basically qualify all the different impacts the cell sees along the line, this lifeline, and to extract the information that we want to mimic in small scale. This is still a challenge, that we qualify from the perspective of the cell what is the most dominating impact that we want to see in small scale, and then to read it. That means to harvest the cells, to analyze the cells, and to see what's happening inside. So this is the most challenging for us, to mimic these large-scale conditions such that the most impactful stresses are mimicked in such a way that we can learn from the cell how they respond on that.
And have you had any highlights so far?
Oh, this is full of highlights.
Yes.
So, I think we managed to say, okay, we do have something like a new, I would like to call it new approach for scaling down the large scale by a small scale reactor in which we insert some disks that, let's say, create artificial compartments and by that deteriorate mixing and such that we mimic large-scale conditions in small scale by, well, low-cost approaches. And that's something that we use right now, and it looks promising. So I think that's a good finding of the first phase of the SPP. And now we are building on that one, fine-tuning it, harvesting, let's say, the setting for doing experiments that are much more mimicking large-scale conditions than we had done before. So that's something new. I would like to call it a success story that we continue thanks to the collaboration with Michael.
And from our point of view, we are very happy that it was possible to integrate first pressure sensors into these sensor particles and to identify areas that are different from other areas in this reactor. We call this compartments. And it was also possible to do some numerical simulations to show these compartments as well. And now we have a much better feeling for these compartments. This is our highlight. And of course, that it was possible to transfer these compartments to Ralf's group and that he could show that these compartments indeed influence the metabolism of the cells. So this was, of course, our biggest research highlight so far. And now we want to introduce more measuring parameters into our sensors. We want to measure pH, temperature, and also concentrations like oxygen or CO2 concentration in future in the second funding period.
And will this research be transferable to a commercial scale?
If you ask me, I say yes.
Yes.
It's the purpose of the whole stuff that we get something in our hands which is adaptable to settings of others, which is laying the foundation of building on let's say case by case studies that are real cases coming from, for instance, the biopharmaceutical industry. That's, of course, one of the targets.
Yes, and I can also only agree on that. This is the idea of the multi-scale approach, because if we are multi-scale, then we understand what's going on all scales. And then we have also the opportunities to go to much larger scale, to industrial scale, and also to other processes.
Well, it's incredibly interesting. Well, I guess we will end here. Professor Dr. Ralf Takors and Professor Dr. Michael Schlüter, thank you so much for being here.
So thanks for that. Thank you.
Yes, thank you so much to give us this opportunity.
Thank you.